Today in this capacity building session, the topic is tunnel, and luckily we have with us a very great speaker, a very great tunnel expert. I'll just give you a brief of Dr. Bineshan Hose. He is basically an Australian principal civil engineer who holds the post of Director Technical at Amber. He is Senior Vice President elect at TAI. So he is B Civil and Mining in Tunnel. He is MSc in Geomechanics. He is MPhil in Civil Structure. He is PhD in Civil Geotechnical, and he is basically an Australian, and he is having 27 years experience in design and construction of road, metro and railway tunneling, hydropower dam engineering, slope stabilization and foundation engineering, and he is providing consultancy and to various construction firms almost in 4 continents. He has developed lot of softwares, lot of method, and one of the system that he has developed is I system, which is basically a comprehensive classification and characterization system for ground, which was developed in 2019. And finally he developed a software which he calls ITM, a complete tunneling method, in 2021. Now he this developed his software again, and then he modified the software, and finally Dr. Bishan I system has been incorporated in Indian Railways construction manual by Ministry of Railways. Both his software, there are two systems, one is I system and another is software which he calls ITM. So Indian Railway has incorporated this, and they are designing tunnels in Himalayan region based on this system. So we are lucky to have him today as a speaker. But before I hand over this mic or this presentation to Dr. Binishan, we must understand that what system currently we are following. So if you see your specification that we are currently following, we are following normally RMR and Q system of tunneling. So let us basically understand what this system is, because a lot of people must not have been involved in tunneling method. So primarily what we do is we classify the rock. When we start tunneling, we classify the rock based on the kind of rock that we encounter. And there are standard systems based on, one is RMR, another is Q system, another is RQD system, one is Terzaghi rock load factor system. So you classify the rock, and then these are all empirical method on the basis of which they have devised the support system that you are supposed to provide as you proceed with tunneling. So depending on the rock you encounter, from a table you can decide, okay, at this location we have to go for shotcreting, at this location we have to go for bolting. All those kinds have been provided. So I'll just give you a brief on RMR system, which normally we are following in NHI. So for all these classification, normally we need to investigate the kind of rock or soil that we are going to encounter. So we go for boring, and there are other methods. We take the sample and then we decide the system. We rate the system, and then we decide the support system that we are going to provide. So just a brief on RMR system. This RMR classification rock, we have to classify the rock that we encounter. So this is basically based on 6 factors. One is, as we can see, it is on the screen, uniaxial compressive strength of rock material that we are going to encounter. Second is rock quality designation, that is RQD. Then we have spacing of discontinuities, कितने कितने दूरी पे discontinuities आ रहा है. Condition of discontinuities friction कितना है, it is likely to slip or not likely to slip, काफी रेसिस्टेंस दोनों के बीच में. ग्राउंड वाटर कंडीशन कैसा है, and orientation of discontinuity, which is again a very important thing. So on this basis we classify the rock that we are going to encounter, which we are currently following normally. So rock mass is divided into a number of structural regions, and each region is classified separately. As we proceed during tunneling, suppose we have a 1 kilometer tunnel, we are going to encounter different rock system. So every system is classified, every location is classified. Normally boundary of such regions, जो region होता है, usually coincide with the major structural features such as fault or with a change in rock type. So we have fault as we proceed further, or maybe there is a change in rock itself. So those becomes the boundary, and for this complete stretch we have one classification system. If there is significant change in discontinuity, spacing or characteristics within the same rock system, suppose we encounter granite but we find there are some changes, we have a lot of fissures, lot of fractures, we may decide to divide it further into small structural regions. This is how we proceed in RMR system. Now if you see this RMR system, it is not only in RMR, but most of the system is using RQD. You must have heard of this term. This RQD is being used by almost all system. Now coming to RMR system, if you see this RMR system, नहीं, पीछे 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 ठीक है previous slide. So these are different six, we can say, characteristics that we are taking, that we have discussed. Next one. Next one. PK next.
हाँ सर, I'm trying.
कुछ प्रॉब्लम हो रही है वेबएक्स में. Okay. Now, as I mentioned, we are dividing this rock mass into different region, and then different region are classified as per the RMR system. Next वाले में चलिए. This is RQD. Now RQD is a common factor in most of the system, which you must be finding that people are calculating this RQD value. RQD is Xi divided by L. What is Xi? It is the length of individual pieces of core which is more than 10 centimeter. So you take a core, suppose in this example, as I mentioned, we are taking a 200 centimeter length core. So whatever core is more than 10 centimeter length, that core is taken. You add those sums. Suppose we have a core of 11 centimeter, we have a core of say 15 centimeters. So all these are added, and that divided by 200 into 100 gives me RQD percentage. And based on RQD, we have another system of classification where we say if RQD is less than 25, it becomes very poor. If it is 25 to 50, it is poor. And similarly, excellent in case we get an RQD of 90 to 100. If we get 100 means it is a complete one piece of rock of total 200 centimeter length. This is what is indicated by RQD. Next. Now, based on this, RMR system was developed. So we saw we have a different factors. Now, if you see this, if you see one in this table, classification of parameters and their ratings. So some rating is given to different factors. First is strength of intact rock. So for this, we find point load strength index and uniaxial compressive strength. Now in this table, if you see that point load strength index, if it is greater than 10 MPa, and uniaxial compressive strength, if it is more than 250 MPa, we give it a rating of 15. Similarly, if you go to next column of range of values, if it is between 4 to 10 and 100 to 250, we give it a rating of 12. In this way, different rating is given for strength of intact rock material. Second component that we mentioned was RQD. So if RQD is between 90 to 100%, we give it a rating of 20. Similarly, spacing of discontinuities, if it is more than 2 meter, we give a rating of 20. Condition of discontinuities, very rough surface, not continuous, no separation, unweathered wall rock, we give it a rating of 30. Similarly, groundwater, we have a system of rating. So we give these ratings, and these ratings are required to be adjusted. So we add these ratings, and these are required to be adjusted based on discontinuity orientation. If the orientation is unfavorable, so we have to adjust whatever rating that we have been given, and that is given in the last row. You can say tunnel and mines, foundation and slope, very favorable, favorable. So you can see it is minus. So if it is unfavorable, we are reducing this rating. This is how this RMR system was developed in 1989, which is the most common system currently being followed. Next slide. So we can see this one example. So what we will see in the next slide, we will see the example. Now on this basis of rating, suppose rating comes between 81 to 100, we give a class number, that rock is class 1. If it is between 61 to 80, we give it class 2. So in this way, classify rock, and in the description, you can see that if rating is between 81 to 100, it is called very good rock. If it is between 61 to 80, it is good rock. Similarly, the last one is very poor rock. Now, if you see what Benswick has given, he mentioned that these set of guidelines are for the selection of support in tunnels in rock for which the value of RMR has been determined. So we determine RMR and what kind of support is required at that location, that is mentioned. These guidelines are produced in a table. I will show you a table. Note that a very important note is mentioned. Note that these guidelines have been published for a 10-meter span horseshoe-shaped tunnels constructed using drill and blast methods in a rock mass subject to vertical stress less than 25 MPa. So there is a condition, whatever classification and support system he has given in the next table that I am going to show is for a specific case, and we are using it at all the locations. Next slide. An example I have taken, suppose point load index is 8 MPa, we give a rating of 12, RQD 70%, 13, and the total rating in this case comes as 59. Suppose in our case at particular location, we get RMA rating as 59. Next. Now based on RMR system, this is the work you are supposed to do. If you see rock mass classification, RMR is 81 to 100, first column. The rock is very good and it is categorized as 1. So in that case, excavation is going to be full face and 3-meter advance. That's how the excavation is to be done, that has been mentioned. Similarly, for a very good rock bolt, the kind of rock bolt, no rock bolting is required. It is clearly mentioned if you are getting RMR between 81 to 100, no bolting is required. Similarly, for different classification, good rock. Now in our case, we got a result of 59. So it is a fair rock and it is coming under category 3. So the kind of excavation, the kind of rock bolting, shotcreting, whatever is required, that is given in the table. And this is how we proceed as we proceed with the tunneling. This is the system that we are currently following. Next slide. So this is RMR system. Similarly, we have Q system, and as I mentioned, we have other systems also. On the basis of RQD, also one table has been given. On the basis of Q, also one table has been given of similar type. So almost all these systems are of same type. So now this system, whether they are applicable in our condition when we are working in Himalayan region or not, that is required to be decided. So as I mentioned, railway at some location they have system to eye system, and I think one example will be given by Dr. Ghosh also. So let us now hear from Dr. Ghosh, who has developed an eye system, which he claims to be more, you can say, appropriate for the condition in which we are tunneling in India. So PK, can you go to the next slide? It's not moving, PK. Yes. So I'll request now Dr. Venetian Ghosh to just share his slide and he can continue with the eye system.
Thanks again for this opportunity. And I would like to start my lecture for today's session, which is about ITM. ITM is Eye Systems Tunneling Method, an A to Z solution for underground works from pre-design to post-construction. I would like to say one brief inside the bracket before going ahead. Today, I will not talk about eye system, only very brief. I will say some introduction about eye system. And if NHA are interested in another lecture, I would be able to deliver a lecture for eye system and comprehensively compare it with other classifications systems. So today focus is on tunneling method, which is ITM, and ITM is the eye systems tunneling method. Today's lecture divided in two main parts. In the first part, I would be having a little introduction about the tunnel design and the tunneling methods. Then I will explain about tunnel design, design approach, eye system, ITM, and design procedure based on eye system. Then I will compare the excavation techniques with tunneling methods. Then I will give more details about tunnel excavation techniques, more details about tunneling methods. Then I will enter to the ITM, including the application, concept, features, advantages, utilization. Then I will compare ITM with existing tunneling methods, including the concepts and principles. And finally, I will talk about iSystem software for ITM that is freely available for everyone to use for design and for construction. In the second part, to have a small break, I will play a film prepared by Indian Railway for USVRL and especially T1, and then I will present the T1 as the case study, including a brief about USVRL project, salient features of the tunnel T1 alignment in Riyasi Trust within the MBT, geological L profile, chronology of failures at T1, advancement flow chart, execution details, overview overview of physical progress in MBT, breakthrough support system employed in main boundary trust. Yes, and main equipment, machineries, and materials employed in MBT, comparison between classification systems. It should be second slide.
You are on table of contents.
Correct, correct.
Okay.
This is the third slide. It is introduction. Is it visible to everyone?
Yes, Dr.
Yes. Existing tunneling methods and design procedure that we are employing in our tunnels are inefficient because they are conservative, incompetent rock. Competent rock is a good rock. That's, for example, in RMR, you saw that it was classified from very good to very poor. Competent rock, competent ground is a good rock, a very good rock, fair rock. Unfortunately, the tunneling methods and design procedure are conservative when the ground is good, and therefore the construction is costly. And finally, the outcome is inefficient. Existing tunneling methods and design procedures are time-some. They are consuming too much time when you're entering to the hazardous ground and you're facing with the incidents, and it causes delayed works. Therefore, again, they are inefficient when you are facing with problems. They are ineffective in incompetent ground, means that in a poor and very poor ground, they are ineffective. Why? Because they are causing unsafe operation. They are not designed for these scenarios. Therefore, again, your tunneling would be inefficient. So, an efficient tunneling method and design procedure required, especially in India, that in the coming years, lots of tunneling projects are opening. Therefore, based on this need, from almost 26 years back, I started to develop a new system, which is called I-System in 2019. I-System-based tunnel design flowchart is this that you see in this slide. It contains 4 main stages. Design approach, which include the empirical, analytical, seismic, and observational parts. Classification and characterization systems, which include I-System, or you may like to use other systems, including RMR or Q. And then you need to have a tunneling method. In this case, and for today, I will talk about ITM, but you may select CTM. CTM is conventional tunneling method. You may select NATM, you may select NMT, or you may select SCL as your tunneling method. Now you are ready for design. And the design procedure based on I-System itself includes 7 stages. DC, which is data collection. GZ, which is ground zoning along the alignments. GB is the ground behavior identification. GH is the associated ground hazards to the ground behavior you have already identified. SS is the support system required for that ground behavior and that specific ground zone. SD is the structural dimensioning, means that dimensioning the required measures for that particular stretch. And SV is the structural verification to prepare the good for construction drawings. Let's go a little bit more into details. In the tunnel design based on I-System, the first is that to select a right approach for your design. Right approach for your design based on I-System includes 4 steps. In the empirical part, we are defining the practicality of design. How practical is the measures we are going to prescribe to client and contractor to implement? Second, analytical part of design, which defines how accurate and precise is our design. Third is the seismic part, how much our structure is resistant against dynamic loaded loads and also the seismic loads. And finally, observational part, which defines the adequacy during the construction. How adequate is your design and prescribed measures? I-system briefly shown in this slide. From left, you see DC. DC is data collection. It includes geohydrological data, geomechanical data, geometrical data, geophysical data, geostructural data, and geotechnical data. All of this data can be collected by eyes, no machine, no equipment required, by engineer or geologist at the face of tunnel or before design of the tunnel on the surface of the mountain. After collection of this data, you will be putting the data into the indices of I-system and impact factors, and you will calculate the I-system. Output would be two. One is the I-class, which is classifying the ground to 10 classes from I1 to I10, means that I1 for the best ground and I10 for the worst ground. And the value of I varying between 100 to 0. In the I-class or classification output of I-system, it will be providing you support system you require to advance, excavation technique that make your advancement safe, instrumentation technique, IT, which require to control the deformation and monitor the deformation, PT or prevention technique that refrain collapses and incidents, FT or forecast technique that propose how to predict the ground from ahead of the faces, and finally design remarks, how redesign your faces while you are moving ahead. The second output of the I-system is IGC. IGC stands for I-systems ground characterization. It provides you with 6 important parameters: modulus of deformation, e.g. nu-G Poisson's ratio, sigma CG compressive strength, sigma TG tensile strength, CG cohesion, phi G friction angle. With these parameters, you would be able to design the structure from A to Z. The output for underground structures called ITM. Output of I-system for underground structure is called ITM, while for semi-surface structure and surface structures is different. ITM holds 2 main principles: assumptions and principal procedure. The assumptions in ITM or I-systems tunneling method is that arch pressure effect at any depth is considered. It never been neglected. Comprehensive application at any ground, controlled release of deformation, flexible contract and management, permanent life for tunnel structure, primary measures as part of final structure, risk analysis and control, utilization of ground's load-bearing capacity. And the principle is that ITM is in a direct contact with the ground zoning, GZ, with identification of ground behavior, GB, with associated ground hazard, GH, with the classification of ground, I-class, with the characterization of ground, IGC, with dimensioning of the structure, SD, with verification of the structure, SV, and very important thing, VID, vibration-induced damage that we induce to the structure during the excavation, which is deteriorating the ground. ITM is controlling it. Design procedure based on I-system itself contains these 7 stages, as I explained in the second slide. DC is data collection, deriving data from ground by geologist or engineer without need of any instruments or machineries. GZ is the ground zoning, property-based congregating of the alignment of tunnel. GB is the ground behavior, identifying mechanical responses for each stretch, for each ground zone. GH is the ground hazard behavior-based failure categorization. SS is the support system determining for ground behaviors. SD is the structural dimensioning each support system. And finally, SV is, which is the structural verification, verifying our dimensioning. Let's enter a little bit more into tunneling methods. In many places, even from the experts, I hear they are using the excavation techniques as tunneling methods. They are totally different. Tunnel excavation techniques are important parts of tunneling methods, but they are not tunneling methods. They are not equal to tunneling methods. Tunneling methods are totally different. I will explain the difference. Tunnel excavation techniques, we can categorize them to 4 main categories. Manual excavation techniques, which is applicable from small to large scale without use of explosives, like partial sequential digging, partial sequential excavation, sequential excavation method, and etc. for head and benching or full face. Mechanized excavation, or ME, is applicable for medium to large scale without use of explosives, like continuous miner, excavator, hydraulic hammer, road header, shearer, and TBM. You may have heard from many people who have worked in the metro, when you say that, what is your tunneling method? They say TBM. This is absolutely incorrect. TBM is not a tunneling method. Tunneling method in metro using TBM is conventional tunneling method. And the machine being used is TBM, tunnel boring machine. So tunnel boring machine is not a tunneling method. It is a machine used in conventional tunneling method. Drill and blast is another excavation technique for tunnels. It is used for small to large scale excavations with explosives, using explosives like residential blast, commercial blast, industrial blast, infrastructural blast, control blast, mine blast, production blast, and uncontrolled blast that in many places in India, I see it is in practice. And it is downgrading and deteriorating the surrounding ground at tunnels. And the last excavation technique for tunnels is the open cut from surface of ground with or without explosives, like area mining or open pit. What is the tunneling method? Methods employed in design, construction, and maintenance of underground spaces called tunneling methods. Tunneling methods employs excavation techniques. Tunneling methods are categorized to 2 main categories. We categorize them medium-based and concept-based. Medium-based is based on the medium in which the tunnels are constructed in. Concept-based, based on the concept that tunneling methods are developed for. Tunneling methods based on the medium categorized in 3 simple categories: rock tunneling, soil tunneling, and underwater tunneling. But based on the concept, it is categorized to 2 very important and determinative classes: civil tunneling and mining tunneling. Civil tunneling is based on the concept of permanent structure, permanently constructed, including ITM, CTM. CTM stands for conventional tunneling method, cut and cover, and ATM, NMT, pipe or box jacking, and SCL, which is standing for sprayed concrete liner. Mining tunneling methods are based on different concepts from the civil tunneling. They are temporary structures, temporarily constructed, including underground mining methods, also ITM, with primary measures only for stabilization for the period of extraction of ore. When you extracted the ore from mine, you do not need this space. You leave it to collapse. But in the civil tunneling, you need this structure to stand at least 125 years, which we call it permanent structure. Now let's enter a little bit more into details of ITM. ITM application in any medium under any condition. ITM doesn't have limitation that I cannot work in the soil or I cannot work in the poor ground. No, ITM can work in any medium, rock or soil or underwater. Under any condition, in any squeezing, swelling, heaving, rock burst, time-dependent, plastic, viscoelastoplastic, or very good and competent rock, in any medium, in any condition is applicable, from pre-design to design to construction, and even after construction in the post-construction phase for maintenance. The concept, as I explained before, is based on these 8 important assumptions. It has never neglected the arch pressure, because if you neglect it, your cost will be increased. It never have any limitation in any medium, so it is comprehensive at any ground. It is controlling the deformation, so deformation will not get out of your control and surprises will not be happened. It is flexible for contract management. It is based on the permanent life for tunnel structure. It is considering the primary measures as part of your final measures, so it is reducing your cost. It is considering the risk analysis and controlling it. It is utilizing ground load bearing capacity, so minimizing the requirement for primary and final measures. What is the features of ITM that makes it different from other existing tunneling methods? It is using I-system in design procedure for classification, for characterization, for ground zoning, for ground behavior identification, for ground hazards identification, for determination of support system, for dimensioning and verification of the measures. Employment of I-system in construction means that during your advancement at phase, in every pool that you get, you will be measuring I-system and you are redesigning in less than 4 minutes and you are moving ahead. Employment of post-excavation damage assessment, only classification, which assess the deterioration that we are applying the surrounding ground during excavation. Implementation of active pre and post excavation support system. As it considers only active measures, it is reducing the measures. So your tunneling would be more optimized. Provision of suitable excavation technique, so you would not be surprised with sudden collapses. Use of efficient instrumentation technique, so you are always alert what is the situation of surrounding ground. Application of intelligent prevention technique, so you are aware what is going on ahead of your faces. Exploitation of high performance forecasting technique. What is the advantages of ITM to existing tunneling methods? Applicability in any medium, rock, soil, or underwater. Feasibility and practicality under any ground condition, covering varieties of ground behavior and hazards. Safety and optimality in design and construction. Cost efficiency, consideration of the primary measures as part of final measures. Uniformity in utilization, because it contains embedded classification and characterization system. Provision for pre-excavation evaluation, again because I-system is there and GCD. GCD is ground conductivity designation. I will explain about this. Recommendation on measures, suitable excavation technique, efficient instrumentation technique, intelligent prevention technique, and high performance forecast technique. provision for post-excavation damage assessment, and provision for flexible contract. How to utilize it? If you are in the design phase, you need to send the geologist on the surface to collect the data, match it with the geophysical and geotechnical data, which is called DC, data collection. Then you will be making a zoning along the alignment. You identify the ground behavior for each individual zone. You find the ground hazards. It's all done by iSystem for each individual zone. Then support system proposed by iSystem, you will dimension it and verify it, and you start the work. When you start the work, for each individual pool length that you are moving ahead, you recalculate the iSystem, and iSystem will tell you what to be done. And it would be repeated, and you are moving ahead without any surprise. This is how to utilize ITM. Let's compare it with other tunneling methods with more details into concepts. If you see the left column, it is in the TMs. TM stands for tunneling methods. CTM stands for conventional tunneling methods. CNC is is cut and cover. NATM, known to you. NMT is Norwegian method of tunneling. Pipe or box jacking. SCL is sprayed concrete liner tunneling method. And ITM is iSystems tunneling method. In the application, as you see, in the phase of pre-design, design, construction, post-construction, only tunneling method which is applicable for entire from pre-design to post-construction is the ITM. Other tunneling methods are inapplicable, except for the construction. In the media, for rock and soil, majority of tunneling methods are applicable only in rock. But ITM is applicable for both of the mediums, rock and soil. Under a special condition means that very problematic condition like Himalayan tunneling. In this situation, none of the tunneling methods are applicable except ITM. You may use other tunneling methods, but you see that how it fails. And today's session with the case study I provide you, you will see that what is the difference. Employing conceptual for permanent life expectancy for the tunnel structure, the only tunneling method which considering this is the ITM. For the flexibility of contract, you will be facing lots of problem with other tunneling methods, but when your contract is based on ITM, you will not be facing with this. So client can manage the contract easily. Surrounding grounds load bearing capacity, only 4 tunneling methods considering it, NATM, NMT, SCL, and ITM. For the arch pressure at any depth, only pipe or box jacking and ITM is considering it. Controlled release of deformation, only ITM considering. And primary measures as part of final measure, only NMT and ITM considering this. Comparing the principles of tunneling method between ITM and other tunneling method, recommendations in construction procedure. None of the tunneling methods provide you the accurate and required support system, excavation technique, instrumentation technique, prevention technique, forecast technique, and stages in construction other than ITM. ITM is the only one which provides you all of these things, even in the construction stage. What is your stages from A to Z? The only tunneling methods which contains classification as embedded in them is only NMT and ITM. Embedded characterization, none of the tunneling method other than ITM. Only ITM provide you the characterization system for design. And for the post-excavation damage assessments, none of the tunneling methods provide you anything except ITM, because in ITM you have VID, vibration-induced damage, which tell you how much you are deteriorating the surrounding ground during your movement. This is iSystem software for ITM. It's very simple based on the data collection by a geologist or an engineer from the face in 10 to 15 minutes and entering the data and getting the output, including all of the support system, excavation technique, instrumentation technique, prevention technique, forecast technique, design remark, and required parameters for even calculation will be given in 4 minutes. Very user-friendly interface and easy to use for engineers, for designers, and for geologists. It's freely available upon request. Before I enter to the case study that I want to explain today, which is Tunnel T1 in USBR project, I would like to play a film for you, which is prepared by Indian Railway, Northern Railway, and KRCL. It takes about 10 to 12 minutes. If it is long, I can shorten it, but I would recommend to have a look at this.
Northern Railway. Konkan Railway Corporation.
The voice is audible, voice of the video, audio.
Yes,
Yeah, we can hear you.
Yeah.
Limited, KRCL, Connecting Dreams with Excellence. Established in 1990, Konkan Railway Corporation Limited is a standout example of excellence in India's railway network. Key highlights.
Engineering feat. KRCL's remarkable achievement is the 741-kilometer-long Konkan Railway, overcoming challenging terrain. Enhanced connectivity, improved travel between Mumbai and Mangalore, promoting tourism and economic growth. Environmental responsibility. KRCL prioritizes eco-friendly practices and safeguards the Western Ghats. Safety first, ensures passenger and freight safety with rigorous standards. Economic impact. Attracts investments, boosts trade, and generates jobs in the Konkan region. Timely execution. The project was completed on time, showcasing efficient management. Technological advancements. Implements modern technology for better railway operations.
KRCL is a symbol of success, sustainable development, and socio-economic progress in the Indian railway sector. Connecting Jammu and Kashmir, the Udhampur-Srinagar-Baramulla Rail Link, USBRL project. The Udhampur-Srinagar-Baramulla Rail Link, USBRL, is a transformative infrastructure project that aims to connect the picturesque region of Jammu and Kashmir to the rest of India through a robust and all-weather railway network. This ambitious project is a testament to the commitment of the Indian government to enhance connectivity, promote economic development, and facilitate easier access to the northernmost state of India. Here are some key points highlighting the significance of the USBRL project. Geographic challenges. Jammu and Kashmir's challenging topography, characterized by steep mountain ranges, deep valleys, and harsh weather conditions, posed significant engineering challenges. Building rail infrastructure in this region required innovative engineering solutions, including tunnels, bridges, and elevated tracks. All-weather connectivity. The USBRL project is designed to provide all-weather connectivity to the region, ensuring that even during harsh winters or adverse weather conditions, people and goods can travel to and from Jammu and Kashmir with ease. This is particularly crucial for the region's socio-economic development and defense preparedness. Economic impact. The completion of the USBRL project is expected to have a profound economic impact on the region. It will facilitate the movement of goods, promote tourism, create job opportunities, and attract investments, ultimately contributing to the socio-economic upliftment of Jammu and Kashmir.
Enhanced mobility. The USBRL project will enhance the mobility of the people of Jammu and Kashmir, making travel safer, faster, and more convenient. It will also reduce the dependency on road transportation, which is often hindered by weather-related disruptions. Strategic significance. The rail link will have strategic significance, facilitating the rapid deployment of troops and supplies to the region, enhancing national security, and bolstering defense preparedness along the border with Pakistan and China. Engineering excellence. The construction of the US Rail involves numerous engineering marvels, including the Pirpanyal Railway Tunnel, one of the longest railway tunnels in Asia, and the Chenab Bridge, one of the highest rail bridges in the world. These feats of engineering showcase India's technical prowess, connectivity to remote areas. The USBRL project aims to connect remote and hitherto inaccessible areas of Jammu and Kashmir, bringing them into the mainstream and providing residents with better access to education, healthcare, and markets for their products. In conclusion, the Udhampur-Srinagar-Baramulla Rail Link USBRL project is a transformative initiative that will usher in a new era of connectivity, development, and progress for the people of Jammu and Kashmir. It represents a significant step toward realizing the region's full potential and strengthening India's strategic position in the northern frontier. As the project continues to advance, it promises to be a symbol of national integration and economic.
I would invite you to pay attention to this part, which is related to our case study today.
Growth. T1 along its alignment in the majority of already excavated length, faced with two main hazards, gravity-driven failure zones and squeezing ground behavior. On 2016, August 28th, at CH32140 of P2, a new unpredicted issue was encountered. The same was encountered on another end, P1, on 2017, March 12th, at CH31804. Faces and above, Chainage's discharged high-pressure mix of debris along with water containing fully saturated, crushed and sheared dolomite, scree, and alluvium and colluvium in a matrix of calcite, clay, and silt. This is the entrance of TO1 to the RT portion of MBT of overcritical wedge of lower Himalayas from both ends.
Since then, till March 1st, 2022, several unsuccessful attempts resulted in 16 failures/discharges with total discharge quantity of over 46,000 cubic meters of debris from faces and formation of a sinkhole to the surface without achieving any advances. This was due to adoption of inapplicable design and methodologies because of misinterpretation of mechanical behavior of ground by designers' employment of inappropriate tunneling methods including conventional and NATM, use of inapplicable rock mass classifications including Q and RMR, and application of unsuitable materials and machineries, which resulted in a huge loss of time, resources, and machineries. Consequently, the client decided to employ new design using new tunneling method and new classification and characterization system after failure of previous designers in resolving the issues with tunneling. Appropriate study in February 2022 using iSystem revealed that the mechanical response of ground at both faces is viscoelastoplastic to fully plastic behavior with almost zero stand-up time. Such stress state requires pre-excavation measures to increase the stand-up time, a pre-excavation solidification technique to enable excavation at faces and prevent discharge, a rigid response to absorb the passive load configuration after excavation, and a special excavation technique to advance at faces of T01 using ITM and iSystem has been done in 6 stages. 1 application of face plug using fiber reinforced shotcrete. 2 conduction of GCD test to measure ground conductivity designation before application of free excavation measures. Pre-application of pipe roofing followed by PU2C injection. or application of pre-injection at face using PU2C. Five, conduction of GCD test to measure ground conductivity designation after application excavation measures. 6, partial sequential digging and excavation and application of rigid post-excavation measures and maintenance of a buttress at face.
This is the T01 in USBR project, which connect the Jammu to Baramulla. Tunnel T01 salient feature contains in this slide, which is 3.2 kilometer tunnel, and the identified ground behavior is fully plastic, gravity-driven liquefaction, squeezing, and viscoelastoplastic behavior. These behaviors are identified by I-System. Before I-System employed, they means that NATM, RMR, and Q, they just identified gravity-driven failure, and better to say that squeezing. Problematic stretches are fully plastic, liquefaction, squeezing, and viscoelastoplastic. And you see that the reason that for 21 years this tunnel was not succeeding was that the ground behavior was not identified properly. In the problematic stretches, they could not be able to move for several decades, for 2 decades. Conventional tunneling method was completely unsuccessful in problematic portions, means that in the fully plastic, liquefaction, squeezing, and viscoelastoplastic section. NATM was also completely unsuccessful in fully plastic, liquefaction, squeezing, and viscoelastoplastic portions. ITM was successfully employed in problematic portion due to failure of conventional tunneling method and NATM. The wetness in tunnel T1 contains from moist, leak, wet, drip, shower, flow, gush, and burst. In the video, you saw that how face was burst during the excavation when they were employing the NATM. None of those incidents happened when they started to use the ITM. Lithology of T1 is claystone, collovium, dolomite, limestone, mudstone, sandstone, scree, shale, and siltstone. And you see that for a stretch of 3.2, this much of difficult ground is really big matter and challenge. Geostructure in tunnel T1 contains highly jointed, highly sheared, and highly tectonite zones. In this slide, you can see the alignment of tunnel T1. This is the revised alignment. And you see that which portion crossing the Riyasi Trust and MBT. Let me explain about Riyasi Trust and MBT. Riyasi Trust is the most problematic portion in MBT. MBT stands for Main Boundary Trust. And Main Boundary Trust is the most challenging and most difficult portion in the overcritical wedge of Lesser Himalayas. And Lesser Himalaya is the most problematic portion in Himalayan ranges. So you can easily conclude that Tunnel T1 at the stretch of 336 meters crossed the most problematic zone of entire Himalayas. The video that you saw and the type of the burst and failure that you saw from the video, it created a sinkhole at the P2 end, which contains 60 meter length, 43 meter width, and 35 meters height. This is the geological L profile. This portion that hatched is the 336 meter length, which representing the Riyasi Trust in MBT. As you see here, chronology of failures are listed here from 2016 to November 2021. And you see that in each incident, they have got several thousand cubic meter of discharge, and in total 47,000 cubic meter discharge was occurred when they were using conventional tunneling method and NATM using RMR and Q. In 2022 March, the task given to Amberg to use I-System for design and ITM for tunneling. Based on I-System and ITM, design prepared, and from May 1st, 2022, they implemented this advanced flow chart. Number one, packing the face with the shotcrete. Number two, conduction of GCD, ground conductivity designation test, to measure conductivity of the face. Number three, application of pipe roofing, followed by polyurethane two-component injection. Number four, application of pre-excavation injection using polyurethane two-component. Number five, conduction of GCD to check if the value of hydraulic conductivity reduced or not. When it is below 1, permission given for excavation. Number 6, and they have moved ahead. In this slide, execution details are shown. A, representing the phase P, how it is conducted and how buttress is maintained. Number B, showing the actual drainage holes, which is not systematic, only in the cases that pressure, hydrostatic pressure was too much. Number C is the wing drainage holes, only implemented when pressure was too much and we wanted to control the pressure. D, representing the GCD hole, D and E, in which direction and how it can be conducted. It is easy, and it can be conducted in 30 minutes. F is the pipe roofing, that with this angle of 5 to 10 degrees, using pipes made in India, not imported, 114 millimeter, conducted for the tunnel. Pre-excavation injection shown in G, that you see how was the pattern. And finally, H, representing the excavation stages, 1, 2, 3, and 4. And 4 is maintained as buttress to control the thrust from the face. This is an overview of physical advance in main boundary truss. I would invite you to pay attention on this slide. Tunneling methods are shown in the left-hand side. When NATM and conventional tunneling method together with Q, when used from August 2016 to August 2019, no progress achieved. and several failures occurred. Totally 1,098 days wasted with total advance of 0 and rate of success 0%. From May 2019 to January 2022, client decided to use an ATM and conventional tunnel method again, but this time with RMR. They have achieved in 984 days only an overall advance of 2 meters. And the rate of success was 0.6%. After unsuccessful attempt, almost for over 20 years, in May 1st, 2022, they decided to switch to ITM using I-System. And they have achieved 564 millimeter per day, total in 596 days, and total advance of 336 meters. And they have done the breakthrough on 20th December 2023 with 100% success and with no failure. This is the breakthrough slide on 20th December 2023. Let's compare the support system employed in MBT in this problematic zone in tunnel T1 in different tunneling methods. CTM stands for conventional tunneling method. Conventional tunneling method for this problematic zone proposed no pre-grouting, no post-grouting, no pre-injection, no post-injection, four-poling, pipe-proofing, systematic bolting, ISHB rigid rib, systematic drainage holes, wire mesh in the reinforcement of the shotcrete, and rebar for final liner. And there was no success. NATM proposed pre-grouting, post-grouting, pre-injection, post-injection, four-poling, pipe-proofing, systematic bolting, use of LG together with ISHB, systematic drainage holes, fiber-reinforced shotcrete, and rebar-reinforced liner with no success. And ITM proposed no pre-grouting, no post-grouting, but pre-injection, no post-injection, no four-poling, but pipe-proofing, no systematic bolting, only ISHB as this rigid rib, no drainage, no systematic drainage holes, only fiber-reinforced shotcrete, and only fiber-reinforced concrete for the final liner with 100% rate of success. Let's see in tunnel T1 which main equipment, machineries, and materials employed in MBT based on the tunneling method. In conventional tunneling method, manual hammer, single action grouting units used as the main equipment. And main machinery contains heavy excavator, heavy jackhammer, wet mix shotcrete pump, and ordinary drill jumbo. And OPC been used for grouting. And special machineries never been used. And that was a good point. But unfortunately, there was no success with CTM. NATM and the two international consultant firm proposed manual hammer, single action grouting units, double action grouting units, TAM grouting system, chemical injection units for main equipment, heavy excavator, heavy jackhammer, wet mix shotcrete pump, ordinary drill jumbo, heavy long range drill as main machineries, OPC for pre-grouting, microfine cement for pre-grouting, ultra-fine cement for pre-grouting, polyurethane silicate for injection, and polyurethane two-component for injection, Casagran PG and Casagran CCXP, which are very expensive machineries, which took 1 year to import, advised in NATM, and there was no success. ITM, from May 2022, proposed manual hammer, chemical injection unit, light excavator, rotary drum cutter, power saw cutter, wet mix shotcrete pump, and ordinary drill jumbo with polyurethane 2-component for pre-injection and no special machineries and 100% rate of success. For your information, 2 international consultants were terminated from T1 due to unsuccessful procedure in design and methodology using RMR, Q, conventional tunneling method, and NATM. And 2 main contractors. Let's compare the tunnel T1's classification system which were used between RMR, Q, and I system. RMR using 7 parameters for classification, Q using 6 parameters, and I system using 27 parameters. In RMR and Q, some of the parameters should be extracted by machines or by some testing methods, but in the I system, there is no testing required, only by geologists or an engineer. And as it contains 27 parameters, precision and accuracy is high. Classification, RMR and Q and I system all are classification system, but RMR and Q are not characterization system. I system is a characterization system also. Independency from RQD. The reason RMR and Q are not successful partly belongs to being dependent to RQD, but I system does not use RQD. And this is one of the key success of I system in prediction of ground behavior. Full measure output, RMR and Q will never propose full measure output, but I system provide you full measure output with method of excavation as well as construction. Performance in problematic condition, RMR and Q, as stated by their developers also, is not applicable for problematic locations and poor grounds, but I system is applicable for any problematic conditions. Accuracy and precision in output. If you send 10 geologists to measure RMR and Q independently, they will come back to you with 10 values. But with I system, never the class that they will be reporting to you would be different because 27 parameters reduce the range of changes and it causes accuracy and precision to be high in classification as well as the characterization. Media's applicability, RMR, Q, and I system all applicable in rock, but for soil, only I system applicable. And in tunneling, in many scenarios, you will be facing with soil, so you would not be able to use RMR and Q for that. Structures applicability for underground, RMR, Q, and I system all applicable, but for semi-surface and surface structures, only I system fully applicable. PL advisor or pull length advisor proposed by I system to give you safe advance and a stable advance in the tunneling. It gives you optimized length, which save you cost, time, and safety. Systematic bolting configurator is the only feature that only available in I system, not in any other classification and characterization system. It is helping you to design any type of systematic bolting, including cone bolting, systematic dynamic bolting, yield bolting, systematic long bolting, and systematic nailing. Vibration-induced damage assessment only includes in I system and ITM, which help you to assess how much you are deteriorating the surrounding ground when you are advancing in tunnel. So you would be able to control it, reduce the cost and time. SRH or stress release hole system only proposed and applicable in ITM, which help you in squeezing, heaving, and swelling tunnels, how to move ahead. If SRH, or better to say, ITM were used in Silk Yara, it could never be happened. It could never be happen, certainly, because SRH not only provide you what is the measures to apply, but also those measures are very low cost and very easily applicable. And also in the maintenance phase, it will help you how to do the reaming. GCD or ground conductivity designation is only applicable in ITM, which is help you to measure the conductivity of ground ahead of the faces to be able to safely drive and to get to know if you are able to move ahead or not. This lecture is done here. The references available with the presentation that I have prepared. If anyone interested to study further about this or have any questions, I would be very happy to help and to respond to all of you with your questions. I'm available by these emails, also through my phone, whenever you are facing with any problem or you want more information about ITM or iSystem. Thank you very much.